Okay, thank you. Just a brief recap in what we are trying to prove. We're trying to prove boundaries for P and one for lacunar means. Okay. As well as the only condition really that we're imposing is the measure is a border measure with compact support has some fully decay. We are seeing the proof. We were motivated by the maximal function, but the analysis is proof of the clinical it's very general setup. Okay, and we replaced the measure sigma by a measure which has cancellation, which is new. Okay, and then we replace the maximal function by a square function, and then by its corresponding singular integrals with the random signs. And we introduce a dynamic frequency decomposition of that measure, and we are proving L2 bonds and weak one bonds. And the L2 bonds are decaying, the one bonds have a logarithmic loss in the frequency. So if we interpolate, we get summability frequencies for the period. If we already saw the L2 bond, then for the with the one bond, we are going to apply the theory of Calderon and Zygmunt, and we are going to verify that this has conformance condition with that logarithmic loss in the frequency. Okay, now the frequency is fixed, and then what we have is that the recurrence KJ are summing overall dynamic scales, which were the relations. Okay, so after the scaling, we already saw yesterday that we can dominate this left-hand side for the programming condition by the sums of this IK, where IK is just this difference in the regularity condition for the kernel, okay? And I just here plug in the definition of my kernel, right? And I can open it up, right? And here there is a convolution of the measure, a little scaling, right? And there's another convolution of the measure with a little very protections, okay? So it has the following form. So of course there's a trivial estimate, right? And I need to prove that only when y is equal to 1 and 2 because of the symmetry of these objects. And of course there's a trivial estimate, right? Which is to do nothing, right? Doing nothing is the measure of compact support, so it's bounded, it's 1, right? And here I can just, these are L1 normalized functions, the frequency projections, so of course the trivial estimates are the IK what we can constant, right? Okay. But of course we can improve on that, right? And when can we improve on that? Well, here we are having the difference to the Beltran projections, and they are evaluated arguments which differ from each other 2 to the minus k times y and y to the scale. So this is really 2 to the minus k. But where are we taking this difference of the Beltran projections? Is the scale 2 to the minus j. Sorry, is a scale 2 to the j. Okay, so in physical side, is a constant scale 2 to the minus j. So as soon as the 2 to the minus k is below, then we can get some benefit from it, right? So this acceleration bound, then tells me that in IK is going to be bound the difference between the two scales. So I put out a j, and then again I benefit from the minus k. So I take minus k. Okay, is this all clear to everyone what I'm doing here? Okay, I'm just writing what this is, and then I have a character here over exponential minus 1, right? And then because okay, and then so of course this is a root bound. Okay, I'm gonna write it artificially in this way. Okay, but this is a root bound if a is greater than j, which means this situation. Okay. And then there's a third bound in which I expect to get some sort of rapid decay or something like that. So we maybe I will give it here. Really well. Okay, now the situation is when we are going to be in the reverse situation, right? That the minus k is larger than the frequency that we have still. Okay, so now I'm not going to get any benefit from this, so I may as well kill it and split it into two intervals. Okay, and so therefore I enter the absolute value here and here and here, so I have the two intervals, and really by doing a very minor change of variables, both terms are essentially equivalent, right? So I can only consider one of the two, and the other one is on analogous, okay? So I'm just gonna skip that to get some time. So then I am hitting off to, let's say, here for instance a factor 2, or essentially a factor 2, and then I'm gonna have the method here. And let's say, and here, and maybe I have to, when I do this state of variables, I have to lose here the 2, but it doesn't really matter, and the y is the theta 1, so I may as well kill it as also, okay, and I can get rid of the y variable. So I can, instead of taking this term, I can essentially take this term. Okay, that's what I'm making. Okay, so okay. So this is like the second term. Okay. Okay. So let me just now write what these two get rid of this scale, right? So this is 2 kilo J D, and then this is beta, and this is 2 kilo J. Right. Okay, now I can do a change of variables to just clean it up. Okay, so now x goes to 3 minus j, right? So I kill off this, and then x goes to 3 minus j, so j comes to the other side. So up until now, I've done nothing other than just visual variable to clean up what the scales are. Okay. So so now I know that the beta has compensatory, right? So that the beta hat, the inverse Fourier transform indicates it must say 1, right? And it indicates the this argument x minus 2 to the j z. But okay, x is larger than 2 to the minus j minus k. So here, and the z lives where? The z lives in the support of the measure of mu. So it's compactly, the measure mu was compactly supported, and the ball in the unit ball, or twice the unit ball, something like that, constant. Okay. So then if k were negative, or like smaller than minus 10, okay, then the x will be way farther than the x minus 2 to the j z. So then really this is comparable to x. So I can kill off it to the j z. Okay. So I only get all the information of the x. And then now that's it. Okay, so is I can control by if the k is negative, or that's no safety, I can modify it as more than minus 10. Okay. X and then x is minus k plus j, right? That's the scale that I'm starting to look at. So that's the data I get when I control this by 1 over 1 plus mod x to be. Okay, so then I get there is a bit like now this doesn't depend on z anymore, so I just say that no one on the measure, which is a constant, right? And then again, the scales in this case is okay. I need to make it negative 1 second. So this goes with what I'm saying, and that's it. I can actually put here as much as I want. Okay. So okay. So this is the bound that compensates with this one, right? So here I get the opposite bound. K is smaller than K, and K is there. Or okay. So so with this the estimate I have one, right? Okay, because if now we can say well it doesn't really matter. So if the J were already negative, okay, I just use this one and the cancellation bound. Okay. But if the J were positive, then I would have a range in which I cannot use yet the rapid decay. And in that intermediate range, I have to use trivial estimate. But how many Ks are there? At most there are J, right? Until I can use the other one. So this is why I get the logarithm. Okay. I don't need to write everything. But at some point the logarithm plus because I can use the rapid decay. So that concludes it. Okay. Are there any questions about that?
What is the last equal on the right side?
Let's see. So this is coming because this, okay. Have the control of that.
Okay.
Okay, and now the X is a more.
Okay.
Right. So so this is the bound for the equivalence for lacunar maximal functions when the P is one. And as Adam pointed out yesterday, he learned about the M, so what happens at the and then at the end, when it's currently an open question, whether under translated in the context of the spherical maximal function, is not normal for relevant measure. It is over whether it maps L1 to it.
But what about the radial case? Is it also an open domain? There is no signal.
Good question.
What is the question?
Whether this is open in the radial situation as well. The weak one boundedness of the lacunar sphere.
In the radial case. I think it might. Let me think about that.
I'm not sure.
Okay,
It's a good question to explore.
I'm kind of thinking about this.
Yeah. Sorry. So this is open. Remember this example that we gave yesterday. Then if we type the sum, which is very super, that's admissible. And then if one starts playing with logs, okay, then also like no the usual manipulations with the logs also don't help at all here. Okay? So so then there are no other examples. So like the case of the full maximal function. And yeah, so it's another question. And there are there are some substitutes or trying or like incremental improvements towards the validity of the result in the sense of what is the smallest or closest space to L1 for which we have the differentiability, right? So we have from that origin space to L1, therefore we have the differentiability for that class of functions of a spherical averages. And and this is started there's some literature. Calixto Calderon already in his paper where he proved the equivalence of the for period one, he also had a knowledge space bound. Okay. And it was an L log L. I'm not gonna write into the details. And then there is a Priest and Stein. They've improved on that, and they have an L log L on the unit cube, I think, something like that.
On the what?
For functions supported on the unit cube, I think Priest and Stein they have an L log L type.
Local, yes.
Yeah. I think it goes the unit cube or something. Then I'm doing recipes from our library. And then please include the following strategy as well. That it maps H1 to H1. Okay. And then later, Seeger write that down. Improve these local results. And log L. And then more recently, Planet and Crouch. They in time when estimated the method above, and then they got into other space. I'm gonna put from this. I'm gonna present the proof of the H1 to H1 models. Okay. Because this is closer to the Calderon-Zygmunt arguments that is the goal of the course is somehow to see how Calderon-Zygmunt ideas also give information for singular averages. That's a little bit of theme. I presented already these sort of ideas with Calderon-Zygmunt theory, and here there will be ideas with atomic decompositions, and if possible tomorrow, but I'm being slower than I thought. I will present some Kelterman-Stein maximal function arguments, which is the dual of this here, okay, also in this context. Okay, so regarding this bound, I'm going to present three. So in this paper, there is also the what is a maximal function along the parabola, and then says the proofs are similar. And I'm not going to present the arguments based on this paper, but instead I'm going to present an argument that from Jim and Andreas, which is in Marcinkiewicz centenary volume. So it's also very relative for that. And so the argument actually is much more general than for spherical averages. Let me say a little bit what is the argument. Maybe it's instructive to talk about historical remarks here to understand the statement of the theory. Okay, so over in 96. So he somehow planted the idea of Chris, I think, for trying to more general, wanted to extend the framework and not just for spherical averages, see how general this could be, and then but unfortunately the condition was imposing on the measure was minus d over 2. And then, of course, this has to recover spherical averages. So it was not, it was an alternative, it was a different result, right? That didn't recover spherical averages. Then here, here, one, okay, he did manage to include the spherical averages and over this case by including these to well, maybe let me put it this way. By including these two, then over two. Yeah. But a second condition. Okay. So what is the second condition? Is that for any delta, we need all of delta to the minus n moles of various delta to cover the support of the measure. Okay. So you can see this recovery in the case of the sphere, okay? Because for the sphere we need delta to the minus d minus 1, and then I have decay d minus 1 of the spherical measure. Okay. So in other words, this is telling us, okay, if n is the codimension of, or let's say n is the dimension of the measure of the surface of the manifold that we are taking averages over, then we are going to have this H1 to equal 1 result if the Fourier decay condition is like the dimension of that surface over 2. Okay, that's what the condition is. Okay. So this based on an L2, this condition is like an L2 estimate, right? With my plans. Okay. And the result that I'm going to present is this Seeger result. This was the volume is 111, I think. Okay. Is that the condition 1, which is an L2 condition, can be replaced by an L2 condition. What does it mean to replace by an L2 condition? It means that maybe or so let's try to understand how this condition is telling us. Okay. So if P0 were equal to 2, okay, by Plancherel, this condition and this condition they are the same. But maybe our average is in the case of the spherical maximal functions, that's the same. We know we have it. Okay. However, there are averages which are more singular. And for instance, you go to a curve in R3, and then even if the curve is not generated, the best decay rate that you can obtain is at L2 is minus a third. Okay, so then we would never be able to match that. But it is possible for somebody large P to obtain, or for somebody small P, because this is dual, right, to obtain this result. And as soon as as long as we have it for P0 sufficiently close to 1, then the H1 we can work on the next and the obtain. That this makes sense what this this condition is telling us. Okay. So note that the L2 condition is like this one, because these A's are averaging operators. These, and here I'm considering the average with radius 1, for example. Okay, so if maybe right here. So remember, A, these are averaging operators. So of course, this is always this is always going to be on a 1, right? So if I have something on a 2, then it implies these estimates for P's. Okay? But it might well happen that it is not satisfied with the 2, but it's satisfied for some very small P. Okay. So that's the condition. Okay, also let me mention this condition is the best that one can get for. So one cannot improve. This is optimal. It cannot be improved for averaging operators. You cannot get better than the dimension, and here over P prime. If P prime is close to 1, it will be P if I am close to P. Okay, and that cannot be. And I was maybe hoping to give the example is very easy. If I for P greater than 2, I just get a function to be a neighborhood of the manifold, a delta neighborhood of the manifold, or 2 to the minus j neighborhood of the manifold rather. And then if I am in the dual range, close to 1, I would evaluate on the 2 to the minus j neighborhood of the manifold, and I would just take a one function supported at the origin. Okay, that would be the example. If anyone is interested, later we can discuss. Okay. Okay, so let's start giving the proof of the scheme of the proof of that. Okay. And well, the proof of course is an equal to equal one result, so one actually know some parts of what is one. Okay, so each one is the atomic space, and here it is the proof is based about the characterization of the atomic space in terms of the square function. Okay, and a reason why I like also this proof and why I wanted to present it is because also for LP results, this characterization of atomic then LP is equivalent to HP, right, for P greater than 1. And then having this characterization through square functions, it can give some information that is also very relevant for the problems. Doing the whole decomposition of the function in the atoms, it will take me a little while. Okay, so I'm gonna present what the decomposition is, and then I'll decide whether tomorrow I'll give the argument of how to obtain it or not, or I focus on something else. Okay, but I'll explain what the decomposition is and then how to use it, and then we'll see if I have time to discuss a little bit what this decomposition comes from. But for the ones that are familiar, I use the Beltran square function. Okay. So use these are all things we can go with my function F. Certain values, okay. Normally I like to write another parameter here, but because I'm not giving the decomposition, it doesn't make sense to write what the other parameter is. But typically there's another. Okay. Where these values are these are cubes, okay. Where values are cubes, which are sum. And these functions, AWs, which they are upon the atoms, okay. They are supported in W. or maybe not in W, but maybe in a fixed dialect. I'm gonna write W star as maybe 10 times W if necessary, whatever constant. Okay. Then, and the W's admit the following decomposition that they can be broken into the Yarrick scales. So let me explain what it means. Okay, so these KJs, okay, these are we can think of them as being frequency localized at scale into the J. Okay. More precisely, they can be seen to come from doing a little Ruppelli decomposition of my function F, and then I am breaking it up wherever it's supposed to be constant. So if I am supposed to be constant at the reciprocal scale to the norm J, and then I'm just breaking that into Q's, into the any Q's of that it's a scale. Okay, these are typically in this theory, these are for these are R, and these are like the building blocks that form the atoms all together. Okay. And so I am doing it for all whenever I am under the W's, which are the original atoms. So therefore, I only care about frequencies which are below. So this is why this condition. So to the minus J is the scale of this capital NR, should say what it is. I say okay, this is what the capital means, the scale, the Ionic scale of the Q bar. I use that notation capital. So it's not the sign, it's the logarithmic. Okay. So this has the good properties of sort of like both walls, no? Because I have this frequency decomposition as I like to have, right? But I also have some localized decomposition in space, right? So this is having a good property. This is very useful. Okay. On this side J here, we can feel that they are literally having projections at the scale J, but they have the benefit of being spatially localized. Right? So frequency localized. I can trade off one frequency localization by spatial localization. And then this is good in order to keep support properties things being localized. I can put here as well as the one. So this decomposition comes from we have F can be you can use the Cantor decomposition formula and you start breaking it you can break it into the subatoms, but then I need to sort them out, right? And then to sort them out, I run supper level set of the square function, can consume the decomposition on top of that, and then I get the W's. Okay. I haven't said yet how to recover the function from this. I mean, how to recover the L1 norm of the square function of the function f, which is the H1 norm. That's a fair property. Is that they have good properties. Well, maybe you could have there. So properties. So this is that I can recover the normal the atom by just going through all the dynamic scales, right? Yeah. Probability. But here is that I can recover the H1 norm of my function, which is something like the over norm of the square function by summing the atoms in R2. Okay, because I've done the atomic decomposition through the square function, and that's what I can. Okay. But here we consider the measure. I will apply to she's bars here, and then sum using R2. Okay, and then these atoms have been chosen to so that the union of all the values giving me a sublevel set of this function. And then let's go. Okay, if I have time, I'll discuss it in detail. But I want to focus on how this is useful to obtain the web. And this page work to okay. Does any of this make sense to some extent? Yeah. Okay. Okay, so okay, so for the group, we want to remember what we want to establish. Well, I can use sigma or mu if mu is a measure that satisfies that condition over there, right? You can think the sphere, and you can think of any measure that satisfies them. Okay. Here is a two-degree dilate. Okay. And now my function is other atoms, right? And okay, and typically, if we look at the Calderon-Zimmermann theory, what typical ideas that one uses when one tries to put this in a quantity. So one of them is typical ideas. One of them is to throw away an exceptional set. So for instance, for the weak one inequality for Calderon-Zimmermann theory, we can throw away the union of like dilates of the Q's, right? Because those like have admissible measure, right? So remember these guys. They have been measured by these, and these are mechanical size, so these are admissible. So I can always take it away from the support of the body. So that's typical idea. What's another typical idea is that okay, that we can find, for instance, when we test, when we are proving that the Hilbert transform, for instance, goes from H1 to L1, right? So in that, because we are not, it's not a one inequality, and we don't throw away an exceptional set, some sort of like an analogy in a way that we can think of that goes, if the operator is local, then we can go through some known bound, okay? So for instance, we can go through L2. So because the operator is local means that if for instance, if I were to have T of W has support, the AW is supported in W, so T of W is supported in a T side, okay? So that's what local means, that is not making the support any larger. Okay. So if so, even if I have an L1 inequality, this is typical in the inverse of L1 to L1. What is about two, and then you can use that analogy in order to grab out two, and then you conclude, right? For that part, at least. And what the third idea for the Beltran is that when we are not in one or two, okay, what do we use? Then throwing away this or taking away the local part allows us to use extensions. So we can typical ideas, so let's try to implement them as much as we can for our object and see how far we can get. Okay. So for the implement, there's the second idea that when the operator is local, we can go through L2 or we can go through the boundedness of the. So we have already proven that this lacunar maximal function are bounded P or P greater than 1. For P, yeah, we have already so let's implement L2. Okay, so I have that my function is the sum of all these atoms, right? So when is the operator going to be local? So we break the sum of the A values. I break it into two parts. And then if so here I have a sum in K, right? A sub in K, and then I have this measure which is to the K guided, okay? So then the A W is supported in W, for example, okay? So then the measure is normally supported, so the 2 to the K is supported in a ball of 3 to the K. So if that 2 to the K is smaller than the size of the W, okay, we are not making the support any larger, just larger by a fixed idea. Huh? So in this part, we are thinking that the operator is local. Does everyone see that? That's because we are doing a convolution of so the support is not getting larger. Okay. And this one it can get larger. So okay. But in this one, operator is local. So let's try to focus on here. So I said this is 2, so let me call this term 2, and then the other one will be term 1. Okay. So focus on this second case. Okay, so I go to a binomials, okay, so to a binomials. Okay, now because I'm in L1, now I can apply triangle inequality. Now I'm in 1, so this is fine. And now I sum over all values, okay, and then I get a restriction inside. So the case is to be here is more than the value. Okay. Now just one piece. Guide. Okay, and I don't know this guy is voted in L1, but I know he's voted 2, right? So. I don't know what she does. Then I pick up the measure of the support of this function. The AW was supported in W, then this operator is local, so it's supported also in W. So this is why this is useful, because now I can pick up measure the 1/2. Okay, and now I apply the coordinates in operator. So this gives me the L2 node. And I go to L2 because these are a decomposition and I have to look at L2. Okay. Oh, this was easy. Look now. Okay. So this doesn't have to be part of decomposed, but I mean, it doesn't make any sense to decompose it now without looking at it and understanding what the obstacle is. So let's try to see, let's try to log this and see how far we can get. Okay, and then we'll explain what to do. Okay. Because we have used idea 2, okay? Then we haven't, there are more ideas that come in, right? I mean, but let's try to see how far we can get with the other. Okay? So it's larger. Okay. And I have more information about my operator. Somehow this idea of the cancellation where is included is compacted in that hypothesis. So remember, we can, for the spheres, it's okay. We can either work with a Fourier decay condition on L2, or we can go with the L2 condition. I'm gonna start working with the L2 condition because this is more general. Okay? So that I'm going to use at some point. Okay, so so let me go already to that LP space. Okay, to LP zero space. Very very much. In order to use that hypothesis, I need to have that my function is frequency localized, right? And that's where I can use the benefit of the decay of the spherical measure. And remember that I don't have a structure. I have a structure that I can see them as I can decompose it in all frequencies, right? So let's bring in this decomposition. So use that. Well, the fact that I have here two guides of clinical nature that is not gonna really show up. I'm just replying. Okay, so here the condition I have is that I am, this is my W, well, then I need to have. To look at frequencies such that the reciprocal is below, right? So then I'm, instead of indexing with the frequency J, I'm just gonna index with the fact that we start to go from LW minus N, when N is measuring the distance from LW to the frequency. I'm just really checking the units. Okay. And now that that hypothesis is for fixed time, right? For fixed scale. Okay. It is not has nothing to do with supremum. Okay. So but I don't know how to be on supremum. So I'll do it that it has already shown up, which is replacing the little infinity norm by the little p norm. Okay. Right. Then you do some for quick time and see how far that can get. Okay. And now at this stage, I have this sum n. Okay. And this sum n, if I take it now outside of the sum, and then I can get something with decays in n, then I have what, right? I mean, the critical case is when the n is matched, okay? When the frequency scale is like the length of the value, right? And then if I can get something that gets better as soon as the n increases, okay, this is like the cancellation picture, right? Then we are good. Okay. So and sum n, I'm gonna have some equal to signal both. Okay, we're not so many. This is very okay. Now it's 5. So each of these guys, okay, now they are for them eyes of them, okay, right? And then we have the first in the end of those guys. So here I am ready to apply this hypothesis. Okay, so I'm almost ready to apply my hypothesis, but not quite yet. Okay, why not quite yet? Because I'm still involving because I have this sum in W. I'm still involving many dyadic frequency scales. My hypothesis is I understand how it decays the Fourier transform, so I need to fix the frequency scale. Okay. So now I need to further break. So look at that the frequency scale depends on the size of the W, right? That's how it lies. So I need to further break and quantify what is the size of the W. So I break it as, let's say, L, okay? And I put here L of W equal to value. Okay? And then if I can take this terminal outside, then I'm good. Okay, then I have hypothesis. Now, these are little Perry projections. Okay, so therefore they satisfy this. This is why they are included here. So, what P is 1 and 2, they satisfy this. Okay? If P is 2, this is as a commonality. Right? If P is 1, it's a strong inequality. Okay? And we are here doing an analysis for a P 0 here, which is P 1 and 2. Okay, so I can here use orthogonality of these little Perry projections. Okay, so this is why I was keeping one. Okay, so then by killing this one, I can take something else. So so I can do wait and take something outside, and then I have single thing, and then I have W, and I use R. Precisely like that. Precisely, operating precisely. Spin. And then with one like it. Now I continue with still one of them. These guys. And now I am good because I fix the frequency, right? Fix the frequency. Okay. This one, well, technically this is not frequency localized because it's localized in space, right? But then these are also going to trade off well frequency localization with spatial with a little bit spatial localization using cancellation and so on. So now I can use the hypothesis. Right? But not yet, well, not yet. Yes, I can use it, but we need to be careful. Okay, we need to be careful because this is at a scale. What this is at the scale to the decay. Okay, so let's not try not to be full. And when I use my hypothesis, this was a unit scale, right? So I need to do a further rescaling and then rescale back. Okay, so now hypothesis plus the rescaling. Okay, so these goes to, we've already discussed it sometimes, this goes to unit scale, so here goes up a minus scale over here, right? Sorry, the decay goes in here. So the decay that I get is with the frequency, and now the frequency decay will go here, so it is R2, and then minus K plus N minus LW, okay, this is the new frequency with the decay. It's N, okay, and it's E minus 1 in my case, but I can just think is the co-dimension, okay, of if I have those hypotheses, but I'm correspond with the sphere, okay. Okay. Divided by P0 prime. I have a sum numbers, right? Yeah. Yes. And now this is sum equal to this. Right? Yeah. But no, it is very good, right? Because this has allowed me to what? This has allowed me a decay in the n variable. Okay. On the difference of the scales, this is where the calculation comes in. Okay. So I already have a stability, then therefore I can forget about the end forever. I can assume the end is equal to 0 from now on. So okay, and now here when this frequency is localized, we have a further spatial localization, because then the building blocks, they are cubes at the same scale, so they are of course supported in this joint cube. So I can further take this out. Okay. Okay. Great. And I'm going to kill off this end, okay, so that it doesn't bother me anymore. Okay, because that's okay. And now I look at this expression, and here is where the main idea comes, and therefore I'm going to stop and take it more here. Okay. So so main idea. Okay. I'm gonna to make it more clear. Let's assume that B0 is 2. If not, there's a handler step to just put it in the 2 situation. Okay. Let's assume that the B is equal to 2. Okay. And okay. Then also okay. Also, this is a guy coming from a single frequency. Okay. But remember that the guys coming from single frequencies, they can be put together to get the original L2 norm, right? So it might be this in particular only by the L2 norm is square of the whole line. Okay? If this what to say. And now the L, I can put them up with the W if I want, right? And now it doesn't play any role anymore. I can put here L of W, and then I can sum overall and overall. And W is more than clear. That's this. Okay. So we now need to recover the L1 norm of the function, H1 norm of the function. Okay. So we still have the summing K, which is the reality. So summing K, then now this is taking it literally bigger. So now it comes in here. The power to power, so I can repeat the summing K inside. Okay. So what do I want? If I end up with this quantity, then I'm gonna be good. Okay, because then I can go with it. Okay. So so I want to put some in the box. Some in K. Over all the place, greater than the L produce. And now I have 2 to the minus K minus L will be minus 1 is 0 time. And then for simplicity, comes the connection that here we have this L1. Okay, so the 3 here becomes 2. Yeah. Okay. So I want to end up with here I have alpha to the P0. So I want to end up with just 1 alpha, right? So if I'm able to say that this is smaller than alpha to the P0 minus 1. Okay. And then the measure of W to the 1/2. And then the L2 norm, okay? Then I can sum in W, and then I'm done. Okay. If I'm able to do it. Okay. What does this mean? Let's try to clean this up. No? So in here, I have this K is greater than this set of values. Okay. So this means that this is a small factor, okay? It's more than 1, but it could collapse, it could be 1. Okay. So, and in here I have this factor and I have this factor squared. So this is the same as I don't have it here, and I don't have this here. And the P0 was 2, so this is, I have just 1. Okay. Okay, so if then if this happens, then it would be good, right? I could always sum in the case. Okay, but this sum up to 1. So if this happens, I will be good. But this might not always happen. If it happens in reverse, then it cannot go up to 1. This needs to stop before going to 1. So I cannot go all the way down to a W. This is a geometric sum. So the best I can do is to go down to a certain K greater than, let's say, tau of W. Okay, where tau of W is the one that when I put tau of W here, okay, it gives me precisely what I want. Is that this quantity, okay, it is the reciprocal of the other one. So if I stop there, then I'm good. Okay, and then I can conclude. So that tells me that I have been able to deal with the terms that I have split my sum into 2 parts, right? I have split it into the K smaller than the W and the K bigger than the W. So now this argument in which I use the cancellation, okay, is only allowing me to cover as much, okay, which is only the case that are greater than that tau W, that's a stopping time, okay? And then here we have been able to use argument 3. So that means there has appeared a new term. The new term is when I am greater than the W, so I'm not local, and the one time is smaller than the tau of W, which is when I cannot use cancellation. And I have this intermediate term. Okay? This in a way is reminiscent of the previous proof, but I think that was the previous proof. There was a moment in which like three parts happened. No? One was cancellation, one was local of the operator, which essentially means that we have rapid decay. If it was properly local, we didn't have a rapid decay, and the intermediate part was the logarithmic thing. Now we want to beat over the logarithmic thing. Okay, and because we are in weaker 1, and we are not in a 1, we are in weaker 1, we may hope that maybe, okay, this might be, can this be put as part of some exceptional set that is admissible? Okay, because now I have this case are controlled. Okay, they are controlled. So I might be able to get some information of the measure of the supports and see if this is an invisible part that I can throw away from the next. Okay. Then we'll see tomorrow if we can actually throw it away. Sorry for point.
Thank you, David. Are there any questions or comments?
I have one.
Yeah, please.
When you introduced real pair value, is it always integer?
Yeah, it is because these are using TP45. The W's are the Q's. So this is an integer, and I'm using this data level to quantify this to just go by levels.
Any other questions?
Well, comment that can verify your question that
Yes.
for radial functions, the Lachenary spherical maximal function is weak type 1,1.
Okay.
And it's unbounded from L1 into any Lorentz space L1Q for any finite Q.
Okay.
But if Q equals infinity, weak type 1,1 is true.
Whose result is that?
I don't know, but it might be an old result, but there is a paper that I wrote with Andreas and Steve Weiner, where we looked at these spherical maximal functions with respect to any set of radii, not just lacunary, not just all reals, we looked at anything. And so we wanted to figure out what was happening at the end point. So for every set of radii, we identify a critical exponent where you have LP bounds above and not below. So for lacunary, that is L1. Okay, because of Davids, we get LP for P bigger than 1. Okay, and it's not and so we wanted to understand what is happening for any set of radii at the critical exponent. And so we tested it on radial functions. So we have a paper just about radial functions, and then we sorted out a necessary and sufficient condition on the set of radii, given a set of radii, when it is weak type at that endpoint, when it is strong type, when it maps to any Lorentz space. And so if you plug into our results, which I just checked, the lacunary set into our condition, you see it's true at the end at the critical exponent. So we get results. So it follows from our work, but I don't know, maybe it was well known beforehand.
Right.
It wouldn't be so hard because everything becomes one-dimensional when you the other is pretty explicit.
Good, thank you.
Related to that, to Jim's comment, one of they have also results not just for radial functions, they have later results for general functions, and in there, at least for the convex sequences, okay. So guys that are like that. Okay, and then you dilate. These are the same. Then this is now my set of dilations. So I take supremum over 1D. Where now this is we would think is an intermediate cases between lacunary and full maximal functions. Okay, so lacunary is where this would be here, right? As you were saying, there's a critical exponent, right? But not only for radial functions, for these complex sequences, we managed to see that for the critical exponent, and now depends on alpha, this is weak type PP. When that alpha is greater than 1. But then for the lacunary case, this collapses to H1. It's not like then for P greater than 1, they were able to prove this weak type, very nice weak type endpoint. But for lacunary, as we discussed, it's a kilo open, one can only get the H1. And some of the ideas are like the ones that I presented here.
Any other questions? I heard. Then okay, the weak type 1 is an open question, but what about restricted weak type?
So restricted weak type, okay. I'm thinking, try to not get mixed up. For the full maximal, for the general maximal function, for the spherical one.
No.
That's the situation is in dimension 2 is not, and then in dimension 3 or higher it is. But for the lacunary,
okay, sorry.
But then L1. Okay.
There's results, by the way. It's not quite clear. So sorry. The question is whether the lacunary spherical maximal function is restricted weak type 1-1.
Exactly. Yes.
Right.
Yeah.
Yeah. So yeah, in that case, if you sort of formally think, it looks like restricted weak type is the same as weak type.
Yeah.
Formally.
Yeah.
So, but there's actually a theorem, and this is a theorem that we have. I don't know if we ever put it in some notes, but I certainly have. Terry and I wrote this out. that indeed if you can prove a restricted weak type inequality for the lacunary maximal function, it automatically implies it's weak type. So they are equivalent, but we need, it's not true in general, but there is a general, if your averaging operator is smoothing in any weak sense, then you can show this equivalence between restricted weak type and weak type on one. It's kind of a nice little sort of little lemma. I have some notes on that. I'm not so sure if we're the ones that observed this, but we couldn't find it in the literature, so we wrote it out.
So the last question, can you interpolate from the results we wrote there?
What interpolation? What results? Sorry.
Any kind of interpolation.
Oh, the result. Oh, those results like near the endpoint or whatever.
Yes, from that endpoint, if you can interpolate in P. Maybe this is a naive question.
Yeah, I'm not so sure about this interpolation. I'm not familiar with interpolation with order spaces but
Yeah.
But I wouldn't be too surprised if those recovered for the modernist for bigger than one, right?
Any other comments or questions? Or if not, then thank you very much. I think we have a great day.